Okay, so t-distribution for the difference of two means. We previously learned how to perform a t-test for inference on a single population average. Now we'll do so for the difference of two means. So let's use a motivating example. So suppose a teacher wishes to know if there is convincing evidence that the difference in average scores between two exams, I'm going to call them A and B, is not due to chance. So not written here. I think this statement is actually the data is the teacher gave the same group of students like kind of the same exam, but one was harder than the other or like phrased differently, and we want to see if there is a significant average difference in the scores between the two of them. So this is definitely sort of a hypothesis test kind of idea. We have a research question that we can answer using this difference of two means framework that we've seen before. So let's do our first step. That is always the first step we do whenever we do hypothesis tests, which is just writing out your hypotheses. So here we have that test A is equal to test B, right, as our null. We'll assume that they're correct. And we'll test that against the alternate hypothesis, the claim that the scores of the two of them are not actually correct. And we use an alpha of 0.01. So this was a trick that we learned last time we did sort of these two means being equal or not equal, which is we'll subtract one mean to the other side. To say that their difference is equal to 0 or it is not equal to 0. So recall that our point estimate, our best guess for this population difference is just the difference of the two sample means, right? We don't know what mu of test A and mu of test B are, so our best guess is, of course, the averages of the samples. So we have a point estimate. Step 2 is the easy one. We just assume the null hypothesis. That is that the true population difference is equal to 0. And then step 3 is the hard one, where we're going to try and find the p-value. So let's take a look at our data. Here's a summary of it. We have test A here and test B here. And you can't really see it, but I'm going to tell you these are each nearly normal. And I'm going to say there was a simple random sample, so they are independent. All right? So we want to see if our conditions for inference are met, right? The first thing we always do is we check our assumptions. But what are the relevant assumptions here? If we were doing difference of two means for non-paired data, we would need that each of their sample sizes are greater than or equal to 30. But that's not the case for test B. We only have a sample size of 27. So there was something that we did when our sample sizes were too small. We used the t-test. We used the t-distribution, and we checked the assumptions for the t-distribution. But this is a little different because suddenly we have these two data sets. And just like how we had two data sets last time, if we want to use the t-distribution for two data sets, they both individually have to satisfy the conditions for the t-distribution. So if either sample isn't large enough, use the t-distribution to perform inference. Both samples must satisfy the conditions for the t. Okay? So just like how when we did difference of two means and we needed both of them to satisfy the central limit theorem, right? Doing the same thing here, but we're checking the t conditions and we need both of them to satisfy for us to move forward. So let's do this. Let's check our assumptions. So each observation must be independent. And I think I actually said that this was the case for our data, that they're all independent. I know I kind of said assume the conditions. So these are the conditions. I'm writing them out, but it's pretty clear just based off my problem statement that based off me saying that they are. Sorry, I'm not being a great statistician at this moment in time, but it's still a useful example for us to go through. So both samples must be nearly normal. And again, this is a condition that I said in the problem statement was satisfied. So if we have these two conditions for both of our groups, both of our data sets, we can move forward with inference. I want to tell you here, you remember for t-distribution, we need to know the degrees of freedom, right? I'm going to tell you degrees of freedom is equal to the minimum where NA is the number of observations from test A, and B is the number of observations from test B. Okay, so before degrees of freedom was just n-1, right? But we have two n's here, so what's our degrees of freedom? And the answer is you take whatever is the smallest sample and you -1 from that, or that's equivalent to saying you -1 for both of them and take whatever is smallest, right? So go with your smaller sample size and proceed forward. Further, our standard error, which is just the standard deviation of x bar A minus x bar B, is equal to actually what it was before. this sort of like thrown together standard deviation, right? But we usually don't know the variances of A and B, so we estimate them with the sample standard deviations squared, which are the sample variances. Which here, if you look at our data, I think we had 14 and 20, right? Yeah, so 14 and 20. Just plug them in. Which, if you listen to your calculator, I think is about this. All right? So we have a standard error, and we know our degrees of freedom. Well, maybe I should go ahead and calculate it. So degrees of freedom is equal to the min of 30 minus 1 and 27 minus 1. Which is just 26. Okay, so I have degrees of freedom, I have standard error, my null value is 0, I can calculate a t-score so I can get that probability and find out what my p-value is. So t is x minus mu over sigma, which here is x bar a minus x bar b minus 0, our null value, divided by that standard error, which is going to be 79.4 minus 74.1 if you look back at our table. 2, which is approximately 1.15. So if we wanted our p-value here, we'd look at the sampling t distribution. This is 1.15 up here. And we'd want to find this probability and times it by 2 to get our p-value. Okay? And we do that using Excel. So the p-value for this test would be 2 times 1 minus, because we want the upper tail probability, of t dot dist 1.15 times the degrees of freedom, which was 26, comma 1. So this is the t-score. This is degrees of freedom, which is going to be 2 times 0.1303, or 0.2606. And our conclusion is therefore to fail to reject. Or I guess I should do this the formal way that I've always done it, which is step 4. That equals 0.01 is less than 0.2606, so we fail to reject. Okay, any questions? Do we want to play the game? All right, I will stop.